So for an adiabatic plug flow or packed bed reactor, if I have only a single reaction, so just a one reaction system, and remember it is adiabatic, I can follow two approaches to solve for the PFR. First approach is I can define my variables only as the molar flow rates. That's now of course for a reactor where I don't have pressure drop, so I'm just neglecting pressure drop for now. Then once I have an FA, I can use an algebraic equation to calculate epsilon, and once I have my epsilon reaction coordinate at that point in the reactor, I can calculate the temperature using that approach that was explained in the first lecture video on this theme. This is of course true if del Cp of the reaction was equal to 0. Then I can calculate another algebraic equation for my concentration, which of course will be Fa over Q, and for Cb it's going to be Fb over Q. And now I can calculate my pre-exponential constant using this temperature that is now available because I know epsilon at that point in my reactor. And of course now I can continue and I can calculate my rate of A. I can calculate the rate of B, and I can have my dFA, dW or dV, and my dFB, dV that I return, and I can integrate over a volume range using solve IVP or ODE int. So the approach where we write the energy balance in terms of a differential equation that is illustrated on the slide over here is much easier to generalize when you've got more than one reaction taking place, as what inevitably ends up occurring in reactors that we have to design for real life situations. So please make sure that you're comfortable with both approaches, regardless of whether you have a single or a multiple reaction system. So how we attack this is to say we are also going to do an energy balance, just like we did the mole balance, over a small slice or volume of my reactor. So go and revise how we derive the mole balance for plug flow reactors. And we are going to take the limit as that del V of course approaches 0. So similar to with a CSTR or any general adiabatic system, we can prove that in that little slice that we are now analyzing, there should be no change in enthalpy of the flowing streams from entering the moment it enters the slice to the moment it exits the slice. Once again, the enthalpy of the flowing streams in that slice changes for two different reasons. It changes because there's a change in temperature in that little slice, and it changes because there is a reaction in that little slice. So this is like applying the product rule over here. So we are first going to change the temperature in that slice while we keep the molar flow rate constant, so without considering the reaction. For that part of the term, we need the molar flow rates as it enters the slice. So therefore, along the length of my reactor, there's going to be a change in the molar flow rates depending on whether it's a reactant or a product. And at each point, you are going to use that actual molar flow rates multiplied by the Cp values at that point where it enters the slice in order to evaluate that summation term. So if I now just slowly want to show you what's happening in this last term over here. So over my slice with a volume dV, I just want to know what is the change in the extent of the reaction so that I can multiply that by the heat of reaction to see what is the change in enthalpy of my flowing streams due to that reaction. So of course I then have dE dV, and I know that my dE can be written as what is the incremental change in any of the components that participates in reaction J divided by its stoichiometric number as it participates in the reaction J. So if I now substitute that in there, I end up with an equation that's got this 1 over VI dF of I as it reacts in J dV times del H of my reaction. And we recognize this as simply being equal to the rate at which component I participates in reaction J. So just to illustrate what will happen to this term if we take an actual hypothetical reaction, the dE of that reaction J per volume multiplied by del H reaction. My dE, if I want to write it in terms of component A, will be dF of A participating in this reaction J, just in that reaction, divided by its stoichiometric number there, which will be minus 2. So I'm going to end up with a dF of A as it participates in reaction J, dV, multiplied by the 1 over minus 2. Okay, so I've got that part of my term, and just multiplied by my del H of the reaction. And now I can calculate this del H at any temperature along the length of my reactor using the equation that we showed in video 1 of this theme. So the resultant equation, without making any simplifying assumptions to say this is a linear equation or whatever, says you need to consider everything that comes into the slice and its temperature must change as it moves over the slice. You need to consider sum once for each of the reactions. Choose a component for which you have the rate as it participates in that reaction, divide by the stoichiometric number in that reaction, and multiply by each of the heat of reaction. So for each of my J reactions, I will account once for the heat of reaction. So now I can consider temperature as a dependent variable along the length of my reactor, and I can make this differential equation the subject of that equation. So it will look as follows. How does the temperature change along the volume or the mass? We're going to sort out the units to make sense depending on our independent variable. It will be equal to negative sum over all the reactions, just sum for each reaction once. Choose a component as it reacts in that specific reaction, divide by the stoichiometric number multiplied by the heat of reaction, and divide that by the energy carrying capacity of my streams as it enters that slice in my reactor. So let's apply this differential equation technique for evaluating the change in temperature along the length of my reactor by considering a single reaction that takes place, and let's just use a liquid phase system for now so we don't have to worry about the Ergun equation. We can calculate the pressure drop in our reactor, but that is not going to affect our rate. So now for each of my dependent variables, I have a differential equation that I can apply to see how they change along my independent variable, and in this case I've chosen volume. So let me share how I do this. Maybe you will find it helpful. What works for me is to say, right, I want a DFA, dV, I'm just going to leave out the dV in the nomenclature. I want a DFB, and I want a dt dV. And this equation I know must be equal to RA, this is RB, and this must be equal to minus RA. So I'm going to choose RA. You can also write it in terms of RB, and I can divide it by the stoichiometric number for A in this equation, which is of course -1, multiplied by del H reaction, divided by the sum term. So the sum term is now the variable where I sum for all my energy carrying capacity terms, Fi times Cp. So now I must make sure that I populate all these unknowns in these equations. So first, let us start with Ra. So now I start to build my function. So I know I want Ra is equal to -k times Ca. Oh, genade. I've got two unknowns here. I've got K and I've got Ca. But not to worry. I can calculate Ca just immediately if I go into my function. It is the Fa at that point divided by Q0. This is a liquid phase reaction. So my Q will be a constant that is specified outside of my loop. So Ca, check. I've got an equation for that. For K, I'm going to use my Arrhenius temperature dependence, so that's K is K naught e to the min e over RT. So let's see, this will be a specification, so that's a parameter. Activation energy is a parameter, and temperature is one of the variables, and I will have a variable at that point where I'm busy integrating. Right, so this is sorted. Now RB, I know that RB is equal to negative RA. So sorted. So let's inspect my last differential equation that I want to return. Oh, I need to calculate this sum t term. So now my yellow is in the way, but let's just add an equation there. This sum term must be equal to FA times CPA plus FB times CPB. So this will come in there so that it's handy at the point where I want to calculate that. And my del H reaction, it will either be a constant that is at 298 Kelvin, or I will have to pop in just another equation there, nothing scary, that says this del H reaction is whatever it is at the reference temperature plus the del CP T minus T ref. Running out of space, even on videos. So now I can, if you want to, you can now count the number of equations. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9 equations, and you can count the number of unknowns to make sure that they match. But your Python will complain if it can't find the variables that you are interested in order to calculate the slopes of your differential equations that you are now going to return. So I noticed there are still quite a few. If you would like to write your, use X as your dependent variable along the length of your reactor as you integrate. And of course for a single reaction that is still possible. So if I inspect this equation over here, I must write this rate therefore as a function of X, and from my mole balance for PFR, make sure that you are able to still derive that equation and recognize that equation. Still need the -1 there for the stoichiometric number for A over there, which is a -1. And now I can end up, after I substitute in here, just inspect the slopes, the differential equations that we've got here. If I now have a situation where del Cp of the reaction is 0, two things happen. Del H reaction becomes a constant, so I can take it out of the integral. So I don't have to integrate. This is not a function of temperature. I don't have to move it to the other side of my differential equations. This energy carrying capacity will not change because I have a chemical reaction. So whether I use it at the outlet or whether I use the value at the inlet, that is not going to matter, especially if I use average Cp values. So this energy carrying capacity remains constant. And after integration, what I will notice is that I return exactly that same linear equation for temperature as a function of X that we derived in the first video on this theme. So when this is true, and of course that there I can now write F naught Cp naught. So this is the same as that first previous slide where I just showed calculate, have an algebraic equation then for your temperature at each different value of X. So in this case, your independent variable, in your DE, your independent variable will simply just be equal to X, will be your variable, and then you will just return dx dv, which will be equal to min RA divided by FA naught. Now I need an equation for RA, so I need an equation for CA as a function now only of X. Everything must now in the end just be a function of X. And I need an equation for temperature, which of course will be this linear equation because of the K naught e to the min e over RT in my rate expression. So what is cool to see here when you write your differential equation for temperature as a function of the differential equation for X is that they will follow each other. The rate at which the temperature changes along the volume of your reactor or the slope will be directly proportional to the slope with which x changes with volume. And x, of course, is dx dv is, of course, proportional to the rate. So if I want to plot x versus volume, and I get this kind of a shape, I will expect exactly the same looking equation, shape for temperature as a function of my volume. So regardless of which approach you follow, get x out or get FA, FB and FC out and calculate x afterwards and then construct your plots. Play around with your data to see whether you in fact do agree with this conclusion of mine.